All right. Next one before lunchtime is team number 11. They're going to talk to you about their Drillbotics competition design project. Team 11, take it away.
Good morning. My name is Nate Cannon, and with me I have Bryce Ferrara, Charles Schaub, Mia Rismalia, and Shabana Moore. And together we make Team 11. We were going to be the first ever LSU entry into the Drillbotics competition. So the objective of our project is to design and manufacture a fully automated drilling rig that completes competition objectives by drilling directionally through a homogeneous rock sample using a control algorithm and sensors. So this would have been the 8th annual competition sponsored by the Society of Petroleum Engineers in the DSATS division. This year there was a big emphasis on directional steering with a autonomous control algorithm. We were tasked with reaching 2 3-dimensional targets via input coordinates. There must be downhole sensor implementation. And of course, there was a big emphasis on safety. So our primary customers would have been drilling companies such as Legacy Directional, our sponsor, and secondary customers could have been anybody in the automation industry in the oil and gas field. So here's a look at some of our competition, some local competition, ULL in the bottom left, and last year's champion OU in the bottom right. Here's a look at our design. We decided to go with a 2-motor system with a clutch in the bottom hole assembly that would allow us to drill directionally or straight. So here's a look at our main functional requirements. We were required to imitate full-scale machinery, protect personnel, and to operate autonomously with a control algorithm. The qualitative constraints include that autonomous control algorithm, a safety casing around all moving parts in the rig, manual overrides in case of damage undetected by the control algorithm, and a downhole sensor in the BHA to send data up to the computer. Here's a look at our quantitative constraints. The most important ones are that the bit was not allowed to exceed a 30-degree inclination, a 15-degree azimuth. There was a max displacement of 10 inches, and we were given a budgetary constraint of $10,000.
So taking a look at some of our concept generation and selection, again, we want to design and build a fully autonomous drilling rig. And there were 4 main components of our design that allowed us to stand out from our competition. And they are our trajectory and control algorithm, our hoisting system, our structure material, and our BHA design. So looking at our trajectory and control algorithm, we chose to use the minimum curvature method, which we'll discuss in more detail later on. For our hoisting system, we chose a unique ball screw design and load cell placement. For our structure material, we used extruded aluminum, and our BHA design included a unique bent sub design. Here's a look at our product architecture. Again, on the left is our 3D CAD model shown earlier, and on the right is the actual progress on the build before the shutdown. So looking at some electrical components, there were 5 sensors used in our design. Starting at the top is our true vertical depth sensor. Coming down is our load cell, which was used to measure a compressive force known as weight on bit. Coming down below that is our RPM sensor to measure the RPM of our drill shaft. And at the bottom is our downhole sensor. And we also utilize a flow sensor to monitor flow rate. Looking at some mechanical components, starting at the top left is our hoisting system, which is comprised of our ball screw and hoisting motor. To the right of that is our top drive and hydraulic swivel. And down below is our bottom hole assembly, or BHA, which is attached to our drill bit.
So moving on to our engineering analysis, we started with analysis on our structure. And the stress analysis that we did was looking at the crossbeam holding the majority of our weight components. So we modeled this crossbeam as a simply supported beam with a conservative load of 300 pounds, which is much higher than the weights from all the components. Finding a maximum deflection of 0.0106 inches, and we were able to calculate a bending force of about 9,000 psi which is less than the yield strength of 35,000 psi. During our operation, as the drill string is drilling into our rock, we'll have lots of sandstone debris flying in every which direction. So we decided to put safety casing around our drilling rig, and we had to make sure that the safety casing could contain the rock debris. So we designed it using our impact analysis. So we did impact based on the size of the debris and the force that it would apply to the safety casing. And we were able to find a maximum crack length from the debris at 0.03 inches, which is much less than the thickness of our safety casing. Moving on to tipping analysis, we want to find the maximum force or the minimum force and distance required to tip the structure. So we modeled it both statically and kinetically to find that our max force to tip is about 385 pounds at a distance of 17 inches, and the angle that would cause it to tip is about 56.31 degrees. So moving on to analysis on our hoisting system, like Bryce said, the hoisting is what applies the weight on bit to our BHA, and the weight on bit is a very important measure during operation as it is one of the main components to provide directional control to our drill string. This is a hard value to measure, so we modeled it mathematically at first, and the mathematical showed that as the drill string goes into contact with the rock, there's an exponential weight increase in weight on bit. So we had to look at the forces of this weight on bit to ensure that it wouldn't overstress the drill string. So we did that by summing up all of the weights from the drill string along with any forces due to acceleration, and we got to an approximate weight on bit of 20.67 pounds. So again, ensuring that it won't overstress the drill string, we looked at a few different measures, first being critical pressure, then burst pressure due to our circulation fluid, a critical force from buckling, and we made sure to offset it to mimic our bent sub offset, and then finally a max torque from our top drive motor. And conducting analysis, we found a critical pressure of 11.68 kSI, burst pressure of 9.3 kSI, a critical force from buckling at about 195 pounds, then a max torque of about 4,000 pound-inches. And it was found that our critical load was this critical force. So we set our weight on bit max to a safety factor of 1.5 of that force at about 130 pounds. And comparing that with the previously approximated weight on bit at impact, it is much greater than that weight on bit calculation. Next, in years past, a lot of teams have had issues with vibration of their inner shaft, and we wanted to avoid any vibrational concerns. So we modeled it to find the critical RPM that our shaft could operate at. So the critical RPM that we calculated was about 930 RPM. So we used a safety factor of 1.5 to find a critical RPM of 618. And using this value, we were able to set our top drive to about 2/3 of that value at 400 RPM. Moving on to analysis on our load cell plate. So load cell plate connects our drive nut from our ball screw assembly to the load cell from our top drive assembly. And this load cell plate essentially carries all the load from the rig moving up and down during operation. So we modeled it as a cantilever beam with the maximum force being the allowable weight on bit for the hoisting system. And we calculated a max shear force of about 130 pounds, max bending moment of about 932 pound-inches, a max displacement of 0.8162 inches. And then using the force, we were able to find the force that would require it to fracture or fail. And that came out to be 283.59 pounds, which is about double the allowable weight on bit. So the load cell plate will not fail. Moving on to analysis of the ball screw. Since the ball screw will undergo a lot of loads during operation, I wanted to make sure again that it wouldn't fail. So we looked at two individual load scenarios. First, due to buckling. So all the forces in the Y direction from weight on bit to any additional weights, we were able to find our critical force due to buckling. And that came out to be about 2,000 pounds, which is much greater than the forces in the Y direction of 224 pounds. And then secondly, the torsion from our torque from our hoisting motor, we were able to find a torsion of 66.85 psi, which is much less than the maximum shear strength of the material of 14,400 psi. Next, we moved on to our BHA analysis, first beginning with analysis on the angle of our bent sub. So this is a pretty standard method that they use in industry, where they use L1 as the distance between stabilizer 1 and the second stabilizer, L2 as the distance between the second stabilizer and the edge of the drill bit. They use that in the equation to relate to the build rate, which we set as 2.26 degrees per inch in order us to achieve all of our targets that we need to for the operation. And we were able to find a bent sub angle to be 8 degrees. Next analysis in the BHA is the freewheel clutch. So like Nate said, this is our main component to allow for directional control during operation. And we wanted to ensure that as the clutch is locked in the counterclockwise direction, that the forces don't overcome the design limit of the clutch. So we looked at 3 different considerations. First being torque coming from our top drive. We found it to be 97.54 inch-pounds. Second is the radial load coming from the rotation of the inner shaft. And the radial load that we calculated was 0.753 pounds. And then finally, using the max speed of 400 RPM that we previously calculated, we compared all these with the clutch design limit, and we were able to select a clutch that was much greater than all of these values that we calculated.
For flow-through bit analysis, we first calculated the jetting force, which is just the force that the fluid would be coming out of the nozzles of the bit, and that came out to 0.000168 pound forces. Next, we calculated the hydraulic force, or the hydraulic power at the bit, and that came out to 5.27 times 10 to the negative 7 horsepower, and that's just the power that we have from the fluid coming out of the nozzles. And then the pressure loss across the nozzle came out to 0.0611 psi. For the flow analysis, we're just making sure that our annular velocity is greater than the slip velocity. So the annular velocity is just the speed at which the fluid is coming up the annulus and out of the wellbore. And the slip velocity is the speed that the particles would fall back down to the bottom of the wellbore. So we calculated the slip velocity to be 0.0316 inches per second. And if we make our annular velocity slightly above that, we come up with a minimum flow rate of 0.0148 gallons per minute, which is just below 1 gallon per hour. So for the flow through the valve analysis, we needed the valve flow coefficient, which is simply the flow rate in gallons per minute per 1 PSI pressure drop over the valve. And we came out with a flow coefficient, flow coefficient of 0.0136. And the objective is to just ensure that we get a full flow through the return flow back to the storage, and then we would gradually open the outlet flow in order to get the proper flow rate to the rig. And these graphs are just showing that once we get to 16% openness on that outlet flow, we would have that minimum flow rate that we need to go to the rig. And the pressure loss from the pump up to the top of the rig where the hydraulic swivel is came out to be 8.495 psi. For the fluid analysis, we were able to test our mineral oil in the lab at LSU, where we were able to use a viscometer, and that's how we got the apparent viscosity and the yield point. And we were also able to test the density using a mud balance. For the hydraulic swivel, we're mainly trying to make sure that our flow is consistent going from the outside of the hydraulic swivel to the inside. So in order to maintain that flow, we had to make sure that our perforation area was much larger than the diameter of the shaft, but we also had to make sure that we didn't have too much of a head loss across those perforations. And we came out with a head loss of 0.01 inches, which is negligible compared to the 8 holes that we would have.
So here's a look at the equations we used to govern the position of the bit. In the bottom left-hand corner, delta V is referring to the depth change, delta N is the change in the north direction, and delta E is the change in the east direction. To the right, we have a planar view of what the beginning part of the drill is going to look like. We will have a 4-inch vertical drill to the kickoff point, after which we will have a build section to orient towards the first target, and then a tangential section to reach that first target. Here's a look at the control algorithm logic. To start, we would calculate the lateral distance between the current point and the first target. We would also calculate the radius of curvature and the azimuth required to get to that first target. After we reach the kickoff point, we would calculate the tool face orientation required to get to target 1. After calculating that, we would start the building phase. And as we build, we would survey instantaneously throughout 3 different measurements: the measured depth, the inclination, and the azimuth. With those measurements, we would calculate the inclination from the current point of the bit to the first target. As soon as that inclination and the instantaneous inclination are equal, we would stop building and start tangentially drilling. Once we are tangentially drilling, we will drill straight until we reach the true vertical depth, comparing all the while the instantaneous true vertical depth and the target true vertical depth. Once those 2 are equal, we would calculate the tool face orientation to get to target 2 and start the building phase over again.
Then for the material selection that we did has been done using the SB chart analysis that can be seen on appendix. So for the rig structure, the material is aluminum extrusion because it's simplicity to build for the structure. And then the load cell plate connector, the material is a low carbon steel A36 due to its function as the end load cantilever plate and must support bending without deflection too much and not failing by yielding. And then the third is the inner shaft. The inner shaft has the function as the pressure vessel that must not fail by fast fracture and the yielding. Also, it must be flexible enough to be bent. Therefore, the beryllium copper is chosen as the material and it's free from the sponsor. The fourth is the bottom hole assembly, which must not fail by fast fracture and yielding as the same as the inner shaft. However, it needs to be stiff, and so the team choose the aluminum rod as the material. Then for the top table, the requirement is the same with the load cell plate connector to prevent the deflection. Therefore, the material is chosen is the low carbon steel. Then for the computers table, we want to maximize the stiffness and also has the lowest embodied energy. Therefore, the material is made from the wood. Then for the sandstone box holder, we want to minimize the embodied energy. Therefore, the material is also made from the wood. And the last one is the safety cover. The safety cover is, the material chosen is made from the polycarbonate because it has the highest fracture toughness and it could protect the personnel from the unexpected damage caused by the projectiles object from the drilling processes. For the manufacturing processes, we did 3 methods of manufacturing, which are the cutting, drilling, and joining. For the cutting and drilling processes, we use CNC lathe for making the bottom hole assembly from the aluminum rod, and then we use the grinder, water jetting, and drill press to cutting the carbon steel for making the motor bracket, top plate, and the load cell connector. And then for the joining processes, we use bolts and welding to connect each of the material to build the whole rig structure.
So taking a look at the actual code used for the competition, the code was written using the LabVIEW programming language, and on screen depicts a high-level overview of how the code was structured. So depicted in black is a 3-sequence flat sequence structure, starting with initialize, then to operation, then to close. And inside the operation sequence is where the majority of the drilling process will take place. This includes one large while loop, and inside that while loop is a weight on bit selector, a state machine with 13 states that will be completed chronologically throughout the drilling process. And at the bottom is a section for the IMU data to be used for trajectory calculations. So here's a look at the actual code itself. And recalling from the previous slide, we have the initialize, operation, and close sequences. Inside the operation sequence is our while loop, and inside this while loop is our weight on bit selector, state machine, and IMU data. So taking a closer look at the weight on bit selector, here we utilize local variables to send 3 different speeds to our hoisting motor to control weight on bit. Taking a closer look at our state machine, this in particular is the vertical drilling state, and below this is a bit of code that allows us to move from state to state. And below this, we also utilize local variables to send information to our B-cell write block down here that'll actually communicate that data to our respective hoisting and top drive motors. Moving on to our IMU data section. Again, we have this area used for trajectory calculations. And at the top right is the position tracking graphs that are that will pull information from the trajectory calculations and display them on our GUI. And down below is our accelerometer, gyroscope, and Euler angle data, where we'll take the current and previous iteration values of that data and store them into an array that will be used for the trajectory calculations. So here's a look at our control panel. Starting at the top left, we have where the user would input the three-dimensional coordinates for both targets. Down below, we have information such as what state we're in, the current time elapsed, what command is being sent to the motors, and a relative BHA temperature. Below this are maximum warnings and a large emergency stop button. Here between these two lines is where the Euler angle data will be sent to these graphs for position tracking, and on the right-hand side is different instrumentation information. So moving into testing and validation, starting with our instrumentation, we had two objectives, and that was to test the reliability and accuracy of our code. Starting with the true vertical depth sensor, this was the only sensor that was tested for reliability and accuracy. So the laser, we did this by measuring the laser distance and comparing it to a tape measure, and we ended up being 95% confident. And we did this for 20 tests for a time of about 2 hours. Next, taking a look at these three sensors, we were only able to test them for reliability, but in order to test for accuracy, what we would have done was use, starting with the load cell, is use known weights and incrementally measure the output from the sensor and compare that to our code. For the RPM sensor, we would have sent a specific RPM command to one of our stepper motors and compared what the RPM sensor was reading to that value that we sent. And then finally, for the IMU sensor, we would have used very precise degrees of rotation in all axes and compared that data to our code. And then we plan to do this, run these tests for about 20 per sensor for an estimated time of about 4.5 hours. And finally, the code for the flow sensor was not created before the shutdown. However, it has been created since then, but that means we were not able to test the reliability nor the accuracy of this code. But what we would have done was to run the pump motor at full load and compare the measured flow rate to the maximum flow rate. And we plan to do this for about 20 tests for an estimated time of about 1 hour.
So here are the results of the calibration test for the true vertical depth sensor. The sensor outputs a voltage reading to the computer. So we found the conversion from voltage to length and found it with the, as Bryce said, within that 95% confidence interval, we found it to be very accurate. And so the way that we verified that the conversion factor was correct was at, as Bryce said, at 20 different realistic locations that the sensor would see during an actual drill. We verified that the measured depth was equal to where we were holding the sensor in relation to the table, as you can see with the tape measure. So here's a look at a little simulation that we ran to make sure that the trajectory equations were correct. As you can see, the boxed values of E, N, and TVDC are the output coordinates of the simulation, and they matched with hand calculations on the right.
So looking at some mechanical components, we did validate the top drive motor and drill shaft connection, And we did this by rotating the drill shaft both counterclockwise and clockwise. And we did this for 3 tests. Next, we validated the motor and ball screw connection. And we did this by measuring the distance of the drive nut and how far it moved within 1 minute's time. And we also ran this for 3 tests. And finally, the BHA clutch mechanism was validated by activating the top drive motor both in the clockwise and counterclockwise directions. And this was also completed for 3 tests. So we also validated some of the code from our full sequence structure. Starting with the weight on bit selector, as we can see at the bottom here, the weight on bit measured was greater than the max weight on bit. And this would create us setting the speed and decreasing the speed to 0, which is stored in this array shown here, that would be sent to our hoisting motor. Next, for the IMU array storage, for this particular example, we wanted the current value for inclination to be 0.003 greater than the previous iteration. And as we can see, both of these values were stored in our array.
For the full rig testing, what we planned to do was model the 4 cubic foot sandstone that would have been given to us by the competition by stacking stepping stones one on top of the other and sealing them with a cement mixture. And this, based on the parameter set, would have given us 2 full tests out of that one model. For the safety considerations, our main focus was on the manufacturing safety hazards, which are listed to the left, and then our operational safety hazards were to the right. For the environmental impact assessment, we assessed that the spill container would be able to contain all of our mineral oil that would have been flowing through the system, and we would have contained it and sent it to the nearest waste facility, as well as our rock sample would have been sent to the nearest rock recycling facility. And any excess material that would not have been used would have been donated to LSU.
And then for the budgeting, as the limitation for the competition is about $10,000, as before the COVID-19, the team has spent about $7,300 for the sensor structure, electrical component, and circulation system. And then for the remaining balance, we still have about $2,700. And as post-COVID expensive, we still need about $400, which being said that as the total of our budget is still below $1,000. And then for the schedule, this is the timeline and planning before the COVID-19. And then after the COVID-19, which we cannot continue to do purchasing, testing and validation, and then assembly because as our access to the lab and campus is closed. And then the competition is also being canceled. However, we still could continue to do automation programming and then additional engineering analysis for the report. And then this is the major milestone of our project from the beginning of September until the May. As an important note that as campus closed at 16th of March, we were ready to perform non-drilling tests to show that the functionality of the multiple part of the object. Thank you.
This is the end?
Yes.
Yeah.
Very good. Floor open for questions.